So good morning, friends. Today we are going to discuss time response analysis of first order system in the subject control system theory. So here I assume that you know about standard test signals, and with that background, I am discussing the time response. So as the name suggests, the time response is the study of how output of a system changes with respect to time when it's subjected to change in input. That is when input is changing with respect to time. So this time response classically has two parts. The transient response when output is changing, and after some time output settles down to a steady value. So that response later on is called steady state response. What is a first order system? So first order system is system having highest order of S as 1 in the closed loop transfer function of the system. Apparently, this is the overall transfer function of a first order system, which you can see over here that the highest order of S is 1. It can also be described by first order differential equation. It has only one energy storing element in it. Example, RL series circuit, RLC series circuit. These are the examples of first order systems. Now, how to find out step response, that if we give unit step signal to first order system, how the output is going to respond with respect to time. So this is the standard first order system. And let's assume that input is unit step. So it's a transfer function, its Laplace is R of S is 1 by S. So the output C of S we get as 1 over 1 plus ST into RS. If I substitute the value and simplify, I get output as 1 by S minus 1 over S plus 1 by T. I'm getting in the form so that easily I can have a Laplace inverse. To find out C of T, I have to get Laplace inverse. So when I take Laplace inverse of this expression, 1 by S gives me inverse as 1. And 1 over S plus 1 by T gives e raised to minus 1 by T times T. Right? So this is my output with respect to time. Now, if I plot the output with respect to time, which is given in the equation of C of T, then this is my input, which is changing at t is equal to 0 unit steps. At t is equal to 0, it has suddenly changed to 1. And now output is changing in this fashion. So it does not respond immediately. It takes some time to reach the value 1. So the output is 1 minus e raised to minus t by capital T, which is shown over here. Now, if I want to compare two systems, I need certain parameters. So for that, first is capital T or time constant. So how is it defined? If at t is equal to t, I get system output to be 63.2 or 0.632 of the final value. So I can say that the time at which I get 63.2 of the final output value is system's time constant. Or other way around, if I take the slope of this output curve at t is equal to 0, and the point at which it intersects the final value, that time also is same t, small t is equal to capital T. So time constant is a parameter which shows you how quick or how slow your system is, right? So capital T is time constant over here. Later on, you can say that system approaches and at t tends to infinity, it is reaching the final value 1. But that is infinite time, which is not defined. So what do we say? We say the time at which system reaches almost about say 95 to 98% the final value. That is my limit of the transient response, or I can say system has settled by that particular time. So this is the time at which the output reaches to say 98% of the final value. So that time technically is known as a settling time. And settling time we can mathematically also prove very easily is generally approximately equal to 4 times the time constant. So settling time is giving you the boundary after which steady state is starting, right? So this is the typical time response of the first order system. Now, this was a general example. Suppose I have an RL series circuit like this, then it is an example, classic example of a first order system. So I can write down the differential equation using the Kirchhoff's voltage law. I can take Laplace transform and I get these equations. Now I just have to take ratio of EOS over EIS to get the transfer function. So I can find out transfer function in this, and you can see that it is a classical first order transfer function, right? So this is what is an example of a first order system. So whatever we have learned is applicable to the first order system, that is RL series circuit, right? So now what do you mean by step response of this RL series circuit? So you can see this is the input is EI. So let's say it is changed to a step, say that is a constant DC is applied, and how output across the resistance is changing. That is what I want to study. So here you can see that output changes to a final value over here. I have to assume that EI is 1 volt and output reaches the final value in this particular fashion. So it does not change immediately, and how quickly or how slowly it is changing, that depends on T. So what is T over here? In case of RL series circuit, we have seen in our previous slide that it is equal to L by R. L is inductance and R is resistance of the circuit. So if I want this system to be quick, time constant should be less, and for that L should be low and R should be high. So this is how, if your response is not as per your choice, you can modify it and you find out the parameters which are responsible for it. As if, see, as in this case, we have calculated that L and R are the parameters affecting. So by designing the suitable value of L and R, I can have a quick response, right? So this is how you can study the response, and later on you can modify also. Now, as we have already discussed, the first order time response is having two parts: transient period and steady state period. So the system up to settling time is called transient period. That is output up to transient output changing, and up to T is equal to 0 to T is equal to TS is called transient period. And after that, system has settled to a steady value, so it is called steady state value, right? So this is how the time response study is done for first order system. Now, a requirement for a good first order system is that time constant should be low, and settling time also should be low, so that system settles to the steady value very quickly. And settling time is the boundary of the transient period that we already have discussed, right? So that's all about the first order system and its step response. In next section, we are going to discuss about the step response of a second order system, right? Thank you.